In today's lesson, I'm going to begin by talking about real numbers. I'm going to talk about different types of real numbers, and I'm going to talk about some language that we use when we're comparing real numbers. In order to help visualize these two topics, I'm also going to be using a number line. A number line is a type of graph. So what Candace is going to do is she's going to take two number lines, put them together perpendicularly, and create a new type of graph. And finally in this lesson, Anne is going to talk about all sorts of different graphs that you encounter in school and in everyday real life. In my part of the lesson, I am going to begin by talking about different types of real numbers. Then I'm going to talk about the real number line. I'm going to talk about relationships between real numbers, equals, approximately equals, greater than, less than. And I'm going to talk about everybody's favorite topic, absolute value. So let's talk about types of real numbers. The first type of numbers that almost everybody encounters as they're growing up are what we call natural numbers. And natural numbers are also called counting numbers. And the reason they're called counting numbers is because they're the numbers we use when we're counting objects. 1 apple, 2 apples, 3 apples, 4 apples. These are the natural numbers, also called counting numbers. Then there's a set of numbers called the whole numbers. The whole numbers includes all of the natural numbers, and it includes the number with the whole. That would be 0. The only number that's a whole number that's not also a natural number is the number 0. Sometimes we talk about the set of whole numbers. When we talk about the set of whole numbers, we need to use what are called set brackets. A left set bracket is a left brace, and then we start listing the whole numbers. And then we use our 3 dots to indicate that this pattern continues inside our set, and then we write our closing set bracket. So this is the set of whole numbers, whereas this is just a list of the whole numbers. We can extend our set into what we call the integers. The integers include all of the whole numbers, but the integers also include what we call the opposites of the natural numbers. And the opposites of natural numbers, which are positive numbers, are called negative numbers. So in the set of integers, there's not only positive 1, there's also negative 1. There's not only positive 2, there's also negative 2. For every natural number, there is its opposite, which is a negative number. And altogether, this makes the set of integers. We further extend our set into what we call the rational numbers. Any real number which can be written as a fraction whose numerator and denominator are both integers is called a rational number. Sometimes we express this idea of a fraction whose numerator and denominator are both integers as the quotient of 2 integers. So a rational number is a number that can be written as the quotient of 2 integers. One obvious example would be 45 over 9. I have written the quotient of 2 integers. Let's note that 45 divided by 9 is 5. So 5 is also a rational number, not because it is written as a quotient of 2 integers, but because it can be written as a quotient of 2 integers. Similarly, negative 5 is a rational number because I can write negative 5 as a fraction that has an integer and a numerator, and an integer in the numerator and the denominator. Now, you may not know how sign number division works, but just like if you take 3 and divide by 1, you end up with 3. If you take 12 and you divide by 1, you end up with 12. It's also the case that if you take -5 and divide by 1, you end up with -5. So negative 5 can be written as a quotient of integers. Let's look at the decimal representation of several rational numbers. If we take 3 and divide by 2, 3/2, that's a quotient of two integers, and we write it in its decimal form, the decimal form is 1.5. If we take 7 and divide by 3, 3 goes into 7 2 times with 1 left over, so this is the same as 2 1/3, and 2 1/3 written as a decimal is 2 followed by a decimal point followed by a never-ending string of 3's. This 3 with a bar over it means that the 3 keeps repeating, not 100 times, not 1,000 times, it never stops repeating. This is 2.3333, on and on and on, and if it was 10 hours later, I'd still be saying on and on and on. 10 over 2, that's a rational number. There's the integer 10 in the numerator and the integer 2 in the denominator, and 10 over 2 simplifies to 5. 23 over 7. I need to be really honest with you. I had to get my calculator out before we did this video for me to know what the decimal representation of this number is. And it turns out that the decimal representation of 23/7 is 3.285714. 285714. 285714. 285714. This pattern of 285714 keeps repeating in exactly the same order forever and ever. That's what the bar represents. Now let's make a little observation here. At least in these 4 examples, every time I wrote a rational number in its decimal representation, either the decimal terminated, I just stopped writing digits, 1.5 and 5, or the decimal formed a forever repeating pattern. Here, the 3 repeats over and over and over again. Here, the pattern 285714 repeats over and over and over again. It turns out that any rational number, when written in its decimal representation, has one of these 2 properties. The set of rational numbers, when written in decimal form, consists of all real numbers whose decimal representations either terminate or eventually become a forever repeating sequence of digits. It turns out that there's another type of real number, but before we launch into that, I want to do a little bit of a discussion about the real number line. To create a real number line, I need to start with a line. And on the line, I draw what we call tick marks. And tick marks are what these little marks are right here. And what I need to do is I need to decide a scale for my number line. And what that sort of means is I need to decide what numbers I'm going to associate with each tick mark. Now, a lot of people's natural instinct is to kind of identify where the center tick mark is and to call that 0. And there's nothing wrong with that, but you also need to keep in mind that you don't have to make the center tick mark 0, which we'll see explicitly in a later example. But in this first example, I'll go ahead and make the center tick mark 0. Now what we're going to do is we're going to write the positive numbers to the right of 0. And I'm going to use a scale of 1, which means that the distance between each tick mark is 1 unit. So increasing to the right of 0, I'm going to identify my tick marks as 1, 2, 3, 4, 5, 6, etc. Now what I'm going to do is to the left of 0, in an equidistant sort of fashion, I'm going to write the negative of each one of these counting numbers. -1, -2, -3, etc. So let's make a little observation. The points associated with 3 and -3 are symmetric across the point associated with 0. And what that kind of means is this, that the distance from 0 to 3 is 3 units, and the distance from 0 to -3 is 3 units, but the points associated with 3 and -3 are on opposite sides of 0. Another way you can think about this is if I had a sheet of paper instead of this computer screen, if I folded the sheet of paper across the point that we associate with 0, the points that we associate with 3 and -3 would lie right on top of one another. The points associated with 6 and -6 are symmetric across the point associated with 0. Both of those points are 6 units from 0, but they lie on opposite sides of 0. In a sort of algebraic sense, where we start letting letters represent numbers, we could say that the points associated with x and the opposite of x are symmetric across the point associated with 0. X could be representing any number. The point associated with 4 and -4 are symmetric across the point associated with 0. This idea of distance between a point and 0, that has to do with absolute value, which we're going to talk about later on. Let's plot some more points on the real number line. So far, all we've indicated are the integers on the real number line, but there's a whole lot of points between the integers. For example, there's a point that's halfway between 3 and 4, and that would be associated with the number 3.5, or 3.5. We also could find a point associated with, let's say, -2.8. And the point associated with -2.8 would have to lie somewhere between -3 and -2. But since -2.8 is closer to -3 than -2, we need to make sure that we draw a point that is closer to -3 than it is to -2. Every real number corresponds to a point on the real number line. And every point on the real number line corresponds to a real number. Let's plot some more points on our number line. Let's plot the point 9/2. When we write 9/2 as a mixed number, 2 goes into 9 4 times, and there's 1 left over, so 9/2 written as a mixed number is 4.5. So I want to plot the point that lies halfway between 4 and 5. Notice that in this picture of the number line, I've only indicated the value of every other tick mark. Sometimes we do this for speed. Sometimes we do this just because it makes the picture easier to read. In either case, the scale is still 1 here because each tick mark is representing 1. So when we start counting tick marks, this is 0, this is 1, this is 2, this is 3, this is 4, this is 5. So I need to be halfway between the 4 and 5 tick mark. So I'm going to try and hit the mark as well as I can. And I didn't do as good a job as I might have, so maybe I'll make my dot a little bit bigger. So there would be a point that we would associate with the number 9/2. Let's plot 200. Well, looking at my current number line, I guess I better get up and take a walk, because it's going to be a while till I find the point associated with 200. This is an example of what we call a not-so-good scale, because I don't want to have a piece of paper that's 100 feet long just to plot the point 200. So I'm going to clear away this number line, and I'm going to come up with a different scale. The first thing I'm going to do here is I'm going to identify 0 as a point kind of towards the left of the number line. I don't need to do this, but if I do this, it gives me a lot more room to get the point 200 in there. And now I'm going to count how many tick marks I have. Let's see. I have got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 tick marks to the right of what I called 0. So thinking ahead, if I use a scale of 40, it's going to take 5 tick marks to get to 200. That'd be great. If I use a scale of 50, it's going to take 4 tick marks to get to 200. That'd be great. If I use a scale of 10, it's going to take 20 tick marks to get to 200. That's no good because I've only got 11 tick marks to work with. A scale of 20, that'll give me, what, 10 tick marks to get to 200? I think that's what I'm going to do. Not because it's the right thing to do, it's just because it's what I feel like doing and it'll work. So let's see. The first tick mark to the right of 0 is going to be 20. The second tick mark is going to be 40, then 60, then 80, then 100, then 120, 140, 160, 180, 200. That's the point I want to plot. And just to remind myself that there are negative numbers, I am going to indicate that the first tick mark to the left of 0 is negative 20. Let's plot the point that we associate with the square root of 7. Now, when I start thinking about this, I'm thinking, what number do you square that gives you 7? And I'm thinking, well, I don't know. If I square 2, that means 2 times 2, I get 4. And if I square 3, that's 3 times 3, I get 9. So I don't know what number I square that gets 7. But whatever that number is, it seems to me it's got to be between 2 and 3. Because 2 is the square root of 4, because 2 is the positive number that you square to get 4, and 3 is the square root of 9, because 3 is the positive number you square that gives you 9, and since 7 is between 4 and 9, seems to me to make sense that the square root of 7 would be between the square root of 4 and the square root of 9. Also, 7 is closer to 9 than it is to 4. It's only 2 steps from 7 to 9. It's 3 steps from 7 to 4. So it also seems to me pretty intuitive that the square root of 7, whatever that number is, it's going to be closer to 3 than it is to 2. It's going to be somewhere around here. Now, if we put this number into our calculator, what our calculator gives us, depending upon how many digits our calculator displays, is a whole lot of digits. My calculator said 2.64575131106, which, let's note, is a little bit closer to 3 than it is to 2. Notice that I've got this funny little squiggly sign between the square root of 7 and this decimal representation. The reason I did that is because even though I copied all of the digits off my calculator, this decimal is nothing but an approximation for the square root of 7. Now, you might be wondering, well, why didn't I just find the pattern for the digits and use one of those bars? Well, if you look at these digits, hopefully you're seeing that so far at least, there is no pattern. It's true that the 1 repeated once, but that pattern did not go on forever. And it turns out that this decimal representation will never stop, and it will never form a forever repeating pattern, because the square root of 7 is what we call an irrational number. And if you think about how the digits are behaving in the decimal representation, it's pretty darn irrational. I'm not going to prove to you that this number is irrational. You need to just take it on faith. If you want a proof, you might ask your teacher, and he or she might be able to straighten you out on that. But for now, let's just take it on faith. Since the decimal representation never stops and never forms a forever repeating pattern, it doesn't matter how many digits I write down in this decimal representation, I'm never going to have the exact square root of 7, and that's why we use this squiggly equal sign. Turns out that irrational numbers have another property, and that's that they cannot be written as a quotient of 2 integers. So irrational numbers can be thought of as follows. Any real number which cannot be written as a fraction whose numerator and denominator are both integers is called an irrational number. The set of irrational numbers, when written in decimal form, consists of all real numbers whose decimal representations neither terminate nor become a forever repeating sequence of digits. Let's see some more irrational numbers. Here's a number that I'm sure you're familiar with. It's the number pi. You might remember that pi is the ratio between the circumference of a circle and the circle's diameter. The circumference of the circle is how far around the circle goes, and the diameter can be thought of as 2 radii of the circle. Turns out that pi is an irrational number. It's pretty difficult to prove this. It wasn't even proven until the late 18th century, and when I went online to research it, even I didn't understand what they were talking about. So even I am taking it on faith that pi is an irrational number. But it was pretty easy for me to make that leap of faith, and hopefully it will be for you too. A lot of you might have associated with the number pi the decimal representation 3.14. That's a good association to have as long as you remember what the association really is. And it's not that these two numbers are equal. They can't be equal. 3.14 is a decimal representation that terminates. Pi is irrational. Its decimal representation never terminates. But these two numbers are really close to being equal, and that's what we mean by this squiggly equal sign. Pi is approximately equal to 3.14. So a little bit to the right of 3 on our number line is a point that's associated with the number pi. I checked it out on my calculator before this lesson, and with a lot more digits, pi is approximately equal to 3.14159265359. But even though I wrote down this just truckload of digits, I still use the old squiggly equal sign because this is an approximately equal relationship, not an exactly equal relationship. You know, if we took that number pi and we divide it by 2, according to my calculator, we would get something close to 3.14159265359 divided by 2. But there's no way we would ever know the exact decimal representation of this division, because if the numerator has a decimal representation that never terminates and never forms a forever repeating pattern, then when we start dividing by 2, the division's never going to terminate, and it's never going to form a forever repeating pattern. You know, I saw in the news a couple years back, a couple people with way too much time on their hands figured out 6 billion digits of pi, but even they didn't come close to knowing the exact value of pi in a sense, because 6 billion digits doesn't even begin to show all of the digits in pi. You know, thinking about our simpler approximation for pi, pi is about 3.14, so pi over 2 is about 3.14 over 2, which is 1.57. So a little bit to the right of 1.5, there's a point on the real number line that we associate with pi over 2. So here's some things you ought to remember about types of irrational numbers. This is not an exhaustive list. This is just some irrational numbers. The square root of a natural number is either a natural number or it's an irrational number. For example, the square root of 49, well, we know if we take positive 7 and we square it, we get 49. So the square root of 49 is a natural number. On the other hand, if we consider the square root of 37, well, let's see, 6 squared is 36, and 7 squared is 49, so whatever number you square that gives you 37, it's somewhere between 6 and 7. And there are no natural numbers between 6 and 7. So the only other option is that the square root of 37 is an irrational number. Pi is an irrational number. It's also true that any arithmetic operation, by that I mean addition, subtraction, multiplication, and division, performed between an irrational number and a non-zero rational number results in an irrational number. If I take pi and I add 2, the result is an irrational number. If I take the square root of 37 and multiply by 5, the result is an irrational number. And if I in turn take that irrational number and subtract 59, that result is an irrational number. So every point on the real number line is a real number, and every real number is a point on the real number line. The set of real numbers can be subdivided into two what we call disjoint sets. Every real number is either a rational number or it's an irrational number. No real number is in both of these sets. It's an either-or situation. These sets are called disjoint. The rational numbers have what we call subsets. One subset of the rational numbers are the integers. And what I mean by this word subset is that every integer is also a rational number. Likewise, every whole number is also an integer. And since every integer is a rational number, every whole number is also a rational number. And inside the set of whole numbers, we have the set of natural numbers. So thinking of this subset idea, a number that would be in the rational numbers but not the integers would be, for example, the number 25 over 4. 25 over 4, when it's written in mixed number form, is 6 1/4. 6 1/4 is not an integer because a quarter is not part of an integer. So we can write 25/4 as a rational number, but we can't put it inside the integer box because it's not an integer. On the other hand, let's think where the number 0 goes. 0 is a rational number, so it can go in the rational number box. 0 is an integer, so it can go in the integer box. 0 is a whole number, the number with a whole, so it can go in the whole number box. But 0 is not a natural number. It's not what we call a counting number. So if I was going to indicate 0 on this diagram, it would go right there. And what I'm saying is that 0 is a whole number. I'm saying 0 is an integer. I'm saying 0 is a rational number. But I'm saying 0 is not a natural number. The natural numbers, that's 1, 2, 3, etc. The numbers that are integers but not whole numbers or natural numbers are the negative natural numbers. -1, -2, -3, etc. Let's talk about a couple irrational numbers. As I indicated before, if I take an irrational number like pi and perform some simple arithmetic between this number and a rational number, I will get an irrational number. So if I took pi and multiplied by 2/7, which is a rational number, the result would be an irrational number. I'm going to give you kind of a kooky irrational number. Let's consider this number, 3.12122, 1222, 12222. Hopefully you're seeing this pattern that I'm getting a 1 followed by ever more occurrences of 2. So we could predict what this number is doing later on. So there is a certain amount of repetition to this number. But what's not happening is I'm not getting exactly the same digits in exactly the same order over and over and over again. And when you write a rational number in decimal form, one of two things happens. The decimal terminates, or you eventually get exactly the same digits in exactly the same order. And that's not happening in this number, so this would be an irrational number. Alrighty, let's talk about some relationships between real numbers. What I have pictured here is two branches of a tree, and there's 3 birds on one of the branches, and there's 5 birds on the other branch. And I think we'll all agree there's more birds on the branch with 5 birds than 3 birds. 5 birds is more birds than 3 birds. 5 birds is a greater number of birds than 3 birds. Mathematically, we write that by saying 5 is greater than 3. This symbol right here is called a greater than symbol, and its red is greater than. 5 is greater than 3. Similarly, there's a lesser number of birds on the branch with 3 birds than on the branch with 5 birds. So we say 3 is less than 5. This is called a lesser than symbol. Notice that in both cases, the arrow is pointing to the 3, because when comparing 5 and 3, 3 is the smaller, the lesser number, and the arrow always points to the lesser number. When comparing two positive numbers, the relationship in terms of which is greater, which is lesser, is 100% natural. But it's not quite as natural when you're talking about comparison of two negative numbers. Which is correct? Is -5 less than -3, or is -5 greater than -3? An argument for this second statement, that -5 is greater than -3, could be constructed thinking about debt. If you owe one person $5 and you owe a second person $3, obviously you owe a greater amount of money to the $5 person than to the $3 person. And if we think of debt as negative, then that would be an argument for saying that -5 is greater than -3. But it turns out we're not going to go there. And here's one of the reasons. If we use that type of logic, then how do we compare -5 and +5? The only way we'd be able to make a comparison is in some sort of context. So we need to search some other way for how we're going to get our mind around this. Well, I think we'll all agree that we want positive numbers to be greater than negative numbers. And when we think about our number line, positive numbers always lie to the right of all negative numbers. And it's also the case that if we compare numbers like +3 and +5, the greater number, which is 5, is also to the right of the lesser number, which is 3. So we're going to use this direction on the number line idea to formally define greater than and less than. This will allow us to compare negative numbers to positive numbers, and positive numbers. What we're going to say is that for any two real numbers, a and b, a is less than b if and only if, along the real number line, a lies to the left of b. And we're going to say that a is greater than b if and only if, along the real number line, a lies to the right of b. So let's see this in action. Let's do several problems where we're going to insert the correct inequality sign, and we're going to limit ourselves to 2 inequality signs, less than or greater than. Let's compare -5 and -3. -5 lies to the left of -3. So by definition, we say -5 is less than -3. What if we compare -3 to -5? -3 lies to the right of -5. So we say that -3 is greater than -5. Both ways we wrote it, the arrow is pointing towards the -5. The arrow always points to the number on the left on the number line. Let's compare -5 and +3. I mentioned one of the reasons we're using this model is because we always want negative numbers to be less than positive numbers. And sure shooting, -5 lies to the left of +3, so we do say negative 5 is less than positive 3. Positive 3 lies to the right of negative 5. So we also say 3 is greater than negative 5. Oh boy, 3.14 and pi. A lot of us grow up with an association that these two numbers are equal, but they're not. If we get out our calculator and we look and see what our calculator says for the value of pi, the first few digits it gives us are 3.1416. On the other hand, if I wanted to write 3.14 with the same number of digits, what I would get is 3.1400. Clearly, we can see in decimal form these two numbers aren't equal. They are approximately equal, but they're not equal. In order to determine which is the larger number, I'm going to look and see where's the first mismatched digit. And the first mismatched digit is 3 digits after the decimal point, and in that location, pi has the larger value, so pi is greater than 3.14, or equivalently, 3.14 is less than pi. And what that means in terms of my number line is that whatever point is associated with the point 3.14, since pi is greater than 3.14, it needs to lie to the right of that point. 3.14 is less than pi. Pi is greater than 3.14. So as I just indicated in our last picture, pi lies to the right of 3.14, or equivalently, 3.14 lies to the left of pi. Since these numbers are on the right side of 0, an implication of this is that the distance between pi and 0 is greater than the distance between 3.14 and 0. Let's see what implications that has on the relationship between the numbers negative 3.14 and negative pi. Recall that pi and negative pi are symmetric across 0. That means the distance between 0 and pi is the same as the distance between 0 and minus pi. Likewise with 3.14. The distance between 3.14 and 0 is the same as the distance between negative 3.14 and 0. So let's move our picture over into negative territory there. This time, the fact that the point associated with negative pi is farther from 0 than the point associated with negative 3.14 ends up with a result that negative pi lies to the left of negative 3.14. Or similarly, negative 3.14 lies to the right of negative pi. So negative 3.14 is greater than negative pi. And since negative pi is the point on the left, negative pi is less than negative 3.14. Now, this little example has a couple pretty hard-hitting concepts in it. One is that if you change the sign on the two numbers in the inequality, the direction of the inequality symbol reverses. We're going to save that one for a lot later on. The other idea that I want to focus on is this idea of distance between points and 0. That idea is called absolute value, and that's what we're going to talk about next. So let's talk about absolute value. The absolute value of 4 is the distance along the number line between 0 and 4. And that distance is 4 units. 1, 2, 3, 4. So we say the absolute value of 4 is 4. But there's another number whose distance from 0 along the real number line is 4. And that number would be the point associated with negative 4. So we also say that the absolute value of negative 4 is 4. So the absolute value of a real number x is the distance along the number line between 0 and x. So for example, if I wanted to know the absolute value of -8, I'd need to know how far is it from 0 to -8 along the real number line. And it's pretty easy to figure out that that distance is 8 units, whatever unit we're using along our number line. So the absolute value of -8 is +8. Something that we've seen an example of a couple times is that for any real number, the absolute value of x equals the absolute value of the opposite of x. The absolute value of 3 equals the absolute value of -3, because the distance from 3 to 0 and the distance from -3 to 0 are both 3 units. So let's play our game again, where we're inserting the correct inequality sign using less than or greater than. Comparing -5 and -3, since -5 lies to the left of -3, we say -5 is less than -3. What if we put those two numbers in absolute value bars? Well, I'm going to think about this a couple different ways. The first way I'm going to think about it is this. The distance from -5 to 0 is 5 units. And the distance from -3 to 0 is 3 units. And I think we all agree 5 is greater than 3. So the absolute value of -5 is greater than the absolute value of -3. I could be a little more literal about this. The absolute value of -5 is 5. The absolute value of -3 is 3. 5 lies to the right of 3 along the number line. So 5 is greater than 3. The absolute value of -5 is greater than the absolute value of -3, no matter how you look at it. Let's compare 0 and -3. 0 lies to the right of -3. So we say 0 is greater than -3. What if we put the numbers in absolute value bars? The absolute value of 0, this sometimes throws people for a little bit of a loop. I'll let you know how I think about it. If I start at 0 and I stop at 0, how far have I gone? I've gone nowhere. The absolute value of 0 is 0 because a trip from 0 to 0 is a trip of length 0. On the other hand, if I start at 0 and I take a trip to 3, I've gone 3 units, no matter what kind of unit I'm using on my number line. So the absolute value of 0 is 0. The absolute value of -3 is 3. Since 0 is smaller than 3, or 0 is less than 3, the absolute value of 0 is less than the absolute value of -3. And if you think about this, the absolute value of 0 is less than the absolute value of any non-zero number, because it's always farther from 0 to a non-zero number than it is from 0 to itself. Let's do some true or false questions. Is it true or false that 4 is greater than or equal to -5? This is the first time we've seen this symbol here. It's called a greater than or equal to symbol. And what we want to know is one of these two things true? Is 4 greater than -5, or is 4 equal to -5? Well, obviously, the statement 4 equals -5 is false. On the other hand, 4 lies to the right of -5, so the statement 4 is greater than -5 is a true statement. So it's also true that 4 is greater than or equal to -5. How about the absolute value of 4 is greater than or equal to the absolute value of -5? The absolute value of 4 is greater than the absolute value of -5. What this is asking us is 4 greater than 5? that is a false statement. So the absolute value of 4 is not greater than the absolute value of -5. The absolute value of 4 equals the absolute value of -5. This is saying, does 4 equal 5? That's false. These two absolute values are not equal. The absolute value of 4 is not greater than the absolute value of -5. So the statement that the absolute value of 4 is greater than or equal to the absolute value of -5 is false. How about 3 is less than or equal to 3? 3 is less than 3. Well, that would be false. Or 3 is equal to 3. That would be true. So the statement that 3 is less than or equal to 3 is true. One more example. 5 is less than 5. 5 is equal to 5. 5 is not less than 5. 5 does not lie to the left of 5 along the real number line. So the statement 5 is less than 5 is a false statement. And as promised, that's my last example. So now Candace is going to take her two number lines, put them together, and dazzle you with some graphs.